Hello, my name is Thiago, and the title of my work is a deep reinforcement learning approach for sensor data harvesting by a swarm of UAVs. So, let's start with an illustrative scenario. This is a forest, and this forest has many areas of interest. An area of interest is anything inside this forest that we might want to collect data about. In this case, it might be the position and the movement of native animals or detecting fires. So if we want to get data off of this forest, the most intuitive approach would be to send someone there, a human, to collect the data and write things down, and then bring this data to somewhere where it can be analyzed. Well, this solution isn't very scalable because forests are very large areas, and we would need a lot of time or a lot of people, and that solution isn't really like financially feasible, and also its applicability is limited because we might be talking about a very remote area where weather and stuff is a factor, so this solution wouldn't work. Another solution would be to deploy autonomous sensors on the areas of interest. These sensors are battery powered, or I mean, they're capable of sustaining power without human intervention, and they're also capable of collecting information from the environment around them and collecting information about the areas of interest inside of this forest. Well, then we have another problem because since we're talking about a remote area, we wouldn't expect there to be network connectivity or network infrastructure to transport the data outside of the forest. And if we want the solution to be scalable, the hardware in these sensors will be very limited. They won't have the hardware capacity to access more long-range transmission methods like satellite transmission. So the challenge that we now have is how we can take the data off of these sensors and transport it to somewhere where it can be processed. Well, the solution we're proposing is employing a swarm of UAVs. This swarm, each UAV is autonomous, and it is also it is capable of flying to the sensor locations and locally communicating with each sensor to collect the data off of it. So the challenge then is how we can coordinate the swarm of UAVs to perform this test as fast as possible and as efficiently as possible as well. This forestry scenario, preservation scenario, wherever, it is only one of the possible scenarios where this solution can be applied. The applicability is more general. It can be applied for environmental preservation, for agricultural monitoring, for surveillance, and for industrial use cases and many others as well. Basically, any use case where we have a hard to access area and we want to get data off of it. So the solution we'll be employing for controlling the swarm of UAVs is reinforcement learning based. And before we explain the solution itself, we need to understand what reinforcement learning is. Reinforcement learning is composed of three big steps. The first one is the agent observes the state of the environment. So I need to explain some words in that phrase. An agent is an entity that performs actions, basically, and it lives in an environment. The environment is everything that is not the agent itself, basically. So bringing it back to the illustrative scenario that I just showed you, the environment would be the forest, the sensors, and even the other agents. Basically, everything that is not the agent itself is part of the environment from its perspective. And the state of the environment is a description of the current configuration of the environment. In practice, the state would be a sequence of numbers that describes the environment and has all the information necessary for the agent to perform an action. And an action is how the agent affects the environment. In our use case, the action is movement. So the agents will choose a direction and they will move towards this direction. And because of this action, the environment will transition into a new state, meaning like the environment is not how it was before, because the agent has performed some action and has thus affected the environment. So a new state is observed, and the agent will receive a reward. A reward is an artificial signal that gets fed to this agent, and the reward is how we control the agent's behavior indirectly. So the agent's objective, the agent's sorry, the reinforcement learning agent's objective in this scenario is to learn the actions that maximize the reward obtained through the scenario's execution. I'll explain the reward signal that we're using later, and it will become more clear. But before we move on to that, we need to discuss a bit how this problem scales to a multi-agent scenario, where we have several agents collaborating. So observations are individual, meaning each agent has its own understanding of the environment. We call that an observation. Actions are also individual. Each agent chooses its actions individually, and that doesn't and an agent's actions doesn't affect another agent's decision. But rewards are collective. So this isn't a theoretical necessity, but it fits our problem completely because we want the swarm of UAVs to collaborate for a common goal. If we were to feed them with individual rewards, they would only choose actions that benefit themselves. And we want them to choose actions that benefit the group entirely. So for collaborative use cases, generally a collective reward is utilized. Talking a little bit about related works, the reinforcement learning for scenarios like this isn't an entirely novel concept. So a lot of other authors have studied this concept, but there are some differences uh, with our work in relation to their work. So the main differences is the objective. What we're calling the objective is what the authors want the agents to learn, basically. So a lot of authors focus on some authors focus on the completion time, meaning how fast the agents can visit the sensors. Some try to optimize the trajectory and minimize the number of transmissions. Others focus on energy characteristics, so trying to spend the least amount of energy possible. And others also focus on age of information, which we're abbreviating here as AOI. Age of information is basically a measure of how recent the data that you're collecting is. So in this case, we want to maximize how recent the data is. Another characteristic is continuous action space and state space as well. So for scenarios that, giving a more concrete example, for a scenario like ours that involves UAVs moving through aerial space, it is intuitive that this space is continuous, meaning there's infinite possibilities for where the agents could be. Like we can describe their position as x and y coordinates in Euclidean space, and this Euclidean space is infinite. There are infinite coordinates where the agents can be, and this complicates solutions a bit. So some authors choose to discretize their solutions, meaning they divide this continuous space into a discrete grid where every cell in this grid is a possible position the agent can be. And there are no positions between the cells in the grid. So basically they reduce an infinite space into like a countable number of cells. And this does simplify the solutions quite a bit, but we also think that it hides possible optimal solutions because there's no guarantee that the actual optimal trajectory that the agents should take falls within this discrete grid. So we won't be doing that simplification. We will be using a continuous space for our problem. Some authors also do not study the multi-agent solutions. So they mostly study like a single UAV performing the collection, whereas we are focused on a multi-UAV solution, sorry, a multi-agent solution where several UAVs are collaborating. And some authors also do not consider the existence of UAV communications, but we think it's important for communication to exist between our agents, because we think this will like improve performance. It is intuitive to believe that communication enhances collaboration, you know. Talking a little bit about the main challenges faced in this work. First, it's modeling the data harvesting problem because it must be modeled as a multi-agent problem, which introduces some complexities. It must also be mapped as modeled as a decentralized problem, meaning that each agent is individually controlled. There's not like a centralized entity controlling everyone. And this is necessary because in real scenarios, we're talking about scenarios with limited network infrastructure. So it isn't reasonable to believe that there will be like that it is viable for there to be a centralized entity controlling everyone. So we're studying individually controlled agents. Also, position and movement must be represented by continuous variables. As we've already explained, this increases the complexity of the problem quite a bit. The second main challenge is adapting the reinforcement learning algorithm. This might sound easy because we're using an algorithm that already exists, but our algorithms are not plug and play. You need to perform a lot of work to adapt them to the model of your problem. And also performance varies by algorithms in ways that are not fully understood. So there's a lot of experimentation involved in this process. And third, we want to experiment and evaluate the proposed approach. We want to collect some qualitative measures for the solution's performance. We also want to interpret the experimental results and discuss the scalability of the solution. So let's first talk about the modeling of the data harvesting problem. The state, which is basically the information we're feeding to the agents, information which the agents will use to choose actions. So our state has three main components. The first one is the position of the closest unvisited sensors. Unvisited is an important word here because we're not considering sensors that have already been visited because it's not useful for the agents to know their positions since we are talking about a single cycle problem, meaning that the agents only need to visit the sensors once. So the position of sensors which have already been visited shouldn't be part of the solution. We'll also feed them the position of the closest agents, so they can coordinate properly. And finally, the agent index. This information will make more sense when we talk about parameter sharing a little bit forward in this presentation. But basically, the agent index allows the agents to have identity. We'll talk a bit about this in the future. The action is the flight direction and speed. So this is really simple. The agents choose a direction and a speed and then travel instantly towards this speed, towards this direction at the set speed. We aren't modeling realistic movement or anything like that, but our vehicles are quadcopters and it isn't so unrealistic to consider that they can instantly choose direction and speed. So we will be making this simplification. Our reward has two parts. The first one is a constant small punishment that is proportional to the number of unvisited sensors. So there's a negative signal that lessens as the agents visit more sensors. And there's also a large instantaneous reward for when sensors are first visited. So everything that you're seeing here on this slide was 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 determined by trial and error, basically an experimentation. There isn't really a theoretical proof of the optimal state for a given RL problem. And the actual state is found through trial and error and experimenting with several different possibilities and using the possibility that gather the most the better performance. Okay. So next, we will explain our solution a bit. This is a big diagram, so let's focus a bit on the left, on the simulation part of the diagram. GradeSim XGM is the name of the simulator that we're using. It is a network simulator, event-based, and it's capable of simulating like network connectivity and exchange of messages between nodes. And it's also capable of simulating basic movement. So this simulator was created in the Grades research group, which I'm part of. but it can be used by other researchers as well. But and for us, for this specific problem, it will be serving as a simulation environment for our scenario, for our data collection scenario. And the right part of the diagram concerns the learning part of the algorithm. So the basically everything that's in orange here is an implementation of a reinforcement learning algorithm. The algorithm that we're using is called MADDPG, but we won't explain that in depth right now. We just need to look at the main parts of this algorithm, which are the actor and the critic. So each agent, each UAV in our use case is connected to an actor. The actor is a neural network that receives as input the current state, so the agent's observation of the environment, and gives as output an action. And I know that in this diagram here, it may seem like the UAV and the actor are two different things, but in practice, they reside on the same hardware. So this is only an abstraction, so it is more intuitive to understand. And our objective, as I've said before, is learning based on a current observation. We want to choose that action that maximizes long-term reward. So, but if you know how neural networks are trained, we need an objective, basically something that we need to tune our network to maximize. And in the case of reinforcement learning, so in the case of supervised learning, we have a ground truth, and we train our neural network to simulate, basically to to have outputs similar to this ground truth. In the case of reinforcement learning, there is no ground truth. Uh, we learn through experimentation and exploitation. And the way this learning works is that there is a second entity called the critic. This critic is only a single neural network, and its input is the state of the entire environment and also the actions chosen by every single agent. And the output of this critic is a score, and this score is basically equal to the long-term is proportional to the long-term reward that that action in that specific state will achieve. And the actor and the critic, they learn in tandem. So the actor learn to perform actions that result in the best scores possible from the critic, and the critic learns how to measure and score the actor's performance based on the rewards that they receive from their actions. An important characteristic of this learning framework is that the critic is only necessary during training, because after training is done, the actors can already like independently choose actions based on their current observations, and the critic is not necessary anymore because the actors already have this knowledge. So in summary, we have a simulation, and we use the simulation to collect experiences, and those experiences get fed to a learning algorithm that acquires knowledge from these experiences and then feeds the knowledge back into the simulation, where the agents will now behave in a more appropriate manner to maximize long-term rewards. So for our evaluation, we will be evaluating on 9 different variations of the same scenario, the data harvesting scenario. We will be varying the number of agents between 2, 4, and 8, and the number of sensors between 12, 24, and 36. We chose these numbers to have a good balance between like scenarios where we have constrained resources and other scenarios where we have excessive resources. So as I said before, reinforcement learning involves a lot of exploration and a lot of experimentation to achieve a good solution. The first results that we're showing here is actually results that didn't quite work out, but it's interesting to look at them anyway. So we will see a lot of charts like this on the presentation, so I'll explain it now. Here we're seeing a representation of the agent's trajectory through an environment execution. We call like a single execution of the environment an episode. So this is a trajectory throughout an episode. Each colored line is an agent's trajectory. They always start in the middle of the scenario, so you know where the trajectory starts. And the black axis they are the sensor positions. They don't move, so they are always a fixed. They're always in a fixed position. But it's important to note that each episode, the sensor positions are randomized. So the agents learn to visit sensors on arbitrary positions within the scenario space. So what you're seeing here, sorry, one more information is that the semi-transparent outline that you're seeing around the line of the trajectory is the communication range of the agents. So what you're seeing here in this graph is that every single agent took basically the same trajectory. Like they are all traveling towards the closest sensor position, and this is not quite what we were looking for. We were looking for them to cooperate. The reason that they learn to perform things in this way is because for this exploratory experiment, if you remember our reward, it is composed of two parts: the punishment and the positive instantaneous reward for visiting sensors. For this scenario, we only had the positive reward, and we also had very lax time constraints. This means that like there was no incentive for the agents to perform their task quickly because they were only positively rewarded for when they visited sensors, but there was no reward or punishment related to the time they took to visit that sensor. And under these conditions, they learned to perform the visitation in a way that visited all sensors, but they didn't really focus on doing it quickly. And this showcases a characteristic of reinforcement learning solutions where the agents are quite opportunistic in the sense that they will figure out the simplest way to achieve as much reward as possible. So if your reward doesn't incentivize the agents to perform uh, an action, the actions that you want them to perform, they won't do it. And it's a bit of it's a bit of an experimental process as well, because if you have a reward that is too specific, the performance will also suffer because you will be introducing your biases into the behavior of the agent, because you will be modeling the reward around the specific behavior that you want, and that's not the objective of a reinforcement learning solution. Like you want the reward to represent the quality of the solution, and you're supposed to let the reinforcement learning agents figure out how to best solve the solution. Sorry, how to best solve the problem. So some better results now that we're showing, where the agents collaborate. You can see that they basically split the task of visitation between themselves, with one agent visiting half of the sensors and the other agent visiting the other half. And the punishment part of the reward structure was essential for this solution, uh, because it introduces a time constraint, and the agents figure out that the way that they can solve this scenario as fast as possible is by splitting work between them. And also you can see that the trajectories are quite optimized, and the agents are abusing their communication range in order to have shorter paths. So they don't need to actually travel like on top of the sensors, they travel like between the sensors in a way where every sensor is covered by the communication range eventually. So this was a very good solution. Another interesting behavior is that the the agent's behavior is quite scenario dependent. So here we're seeing two episodes on different scenario variations. The first one is the one where we just saw, with two agents and 36 sensors. And on the right, we have a scenario with 8 agents and 36 sensors. And if you look right here, you can see that two of the agents basically didn't do anything. They just like traveled to the right and they chose the same path, and they didn't really help in solving the problem. And the reason this happens is because, as you can see, the scenario is quite crowded, and maybe we have like an excessive number of agents in this scenario, and uh, and we can see that we're having diminishing returns. And if we look at the actual data, this graph here on the right, it's a bar graph that shows the completion time. So basically the amount of time it took for the agents to complete the scenario for all 9 variations. So we have 9 bars for 9 variations. The blue, orange, and green colors are for the agent count variations, and on the x-axis we have 12, 24, and 36 sensor counts. And if we look at the difference between 2 and 4 agents and between 4 and 8, we can see that the difference between 2 and 4 is very, very big, and the difference between 4 and 8 is very, very small, because uh, so even though we're doubling the number of agents in both cases, we can observe the diminishing returns as the scenario becomes crowded with agents. Another important part of this work, it was the training process. So the reference implementation that we took at the start of this work, it took approximately 30 days to train for our scenario. And after heavy optimization, we were able to get a single model training in 4 days approximately, and everything trained on an RTX 3090 on a VM provided by the department. And this might seem like an implementation detail, but it was actually like the main guiding factor of this work, because developing software is an iterative process. So when you're developing software, you develop something, you make a mistake, you fix the mistake, and you move on. And the time between these iterations greatly affects the development time of the entire solution. And as you can see here, like the time between iterations for our reinforcement learning solution, and for most reinforcement learning solutions actually, especially those that involve deep learning like ours did, the time between iterations is in the scale of days. And if a researcher or whoever is trying to implement a solution and they don't have access to the appropriate hardware, it will take even longer. And this has very big implications on the area of reinforcement learning and deep learning in general, whereas it's very hard to perform to have good results if you don't have the appropriate resources. It is a very the accessibility of the area is very bad in this sense, and this has a lot of consequences in how research is performed. So in order to try to minimize the impact of this training process on our work, we try to develop some scaling strategies. These scaling strategies are divided in 2 categories, basically. The first ones, they try to make the training itself faster, so we can train independent models quickly. And the second category, try to investigate how we could train less models. So basically, we will try to train more general models that perform better, that perform well in more scenarios, and so that we don't need to train as many like models for specific scenarios. The first strategy we tried was asynchronous training. And the way this works is that if you remember that diagram that I showed you earlier, there are basically 2 parts of the solution. The first is the simulation part, and the other is the learning part. The simulation part, which in this diagram we're calling acting, it doesn't really use, so it almost exclusively uses CPU resources, whereas the learning part almost exclusively uses GPU resources. In a normal reinforcement learning training loop, these 2 actions are executed synchronously. So first we act and collect an experience, and then we learn about this experience, and then after learning is done, we act again and we learn again. So it's a synchronous process, and it is quite inefficient when you think about the hardware resources, because half of the time the actor, like the CPU, is idle waiting for the learning to complete, and half of the time the GPU is idle waiting for the acting to complete. And asynchronous training tries to remove this limitation and perform everything asynchronously, and so no part needs to wait for the other one. This also enables us to implement, like, instantiate several actors in parallel. So we have like several simulations occurring at the same time, collecting experiences at the same time. And in principle, this solution is interesting, but in practice, it introduces a lot of complexity to a solution that was already very complex.
And with complexities, I mean like hyperparameters and code that we need to like properly debug, and we also need to perform like exploratory evaluations to find the best hyperparameters. And at the end of the day, we didn't find this a worthwhile investment of time. You can see the best results that we obtained in this chart, in this plot here, and you can see that they're very inconsistent. So for 2 agents, we got a good performance, but for 8 agents, we got like average. It kind of stalled out where it started, and then for 4 agents, the performance completely degraded, and the agents didn't learn anything at all. And we're not disputing that asynchronous training works, but we just didn't find it a worthwhile investment of time for this work. The second strategy that we tried out worked very well. It involved training models that were general to the number of sensors in the scenario. So if you remember, we had 9 scenario variations. A third of those scenario variations, they pertain to the number of sensors. And our initial implementation, it trained a single model for each variation of the problem. That meant that we had to train 9 different models for the results that we showed you before. And what we wanted to do was generalize this model to the number of sensors. So we only needed to train 3 models, one for each number of agents that we were trying out. And this solution actually worked very well. You can see on the graph on the left showcases the performance throughout every sensor count. And this is another advantage, because before we were only testing with 12, 24, and 36. But now we trained a model that is general to any number of sensors between 12 and 36. So if it is 13, 15, or 27 or whatever, the model still performs adequately. And you can see on the graph on the right that the comparison between the previous solution, which is the orange one, named fixed sensors here in this graph, is the performance is very comparable to the varying sensor solution. So we thought that this was a very worthwhile investment of our time, and it has basically no negative impacts on performance, and it reduces the training time by 3 times, basically. In our case, where we were experimenting with 3 sensor variations, but possibly even more if you're interested in models that can perform more generally to the number of sensors. So this was a very good strategy. The next one, we try to generalize to the number of agents. And this is not so easy because of a single characteristic of the algorithm that we're using, which is the critic. If you remember, when we talk about the critic evaluates the agent's performance as a whole, like the entire group of agents. And if the number of agents is changing, the size of the group is changing, and the size of the input to the critic neural network will need to change as well. But neural networks, they require a fixed sized input. So we can't really like just change the input during training. We have to have a fixed number of a fixed group of agents, basically. What we tried to do was manipulate the input of the critic in a way where it worked with a varying number of agents. We did this by filling the missing agents with zeros, and also filling the missing agents by creating like fake agents. Neither of the strategies really worked. And at the end of the day, with this strategy, we're trying to fight against a principle of the MADDPG algorithm that we're using, and this wouldn't really work. But we did point out some other interesting solutions in the text of the thesis itself, where I investigated some other authors' work that is very promising, but they involve like more fundamental tuning of the MADDPG algorithm, or the usage of different algorithms altogether. But one specific work of those that I just mentioned, it actually proposed a very simple solution, so simple that we were able to try it out on our problem. And the solution is so what the author is proposing is that the number of agents during training doesn't necessarily need to be the same as the number of agents during deployment. Maybe the author proposes that maybe like if we train a scenario with 2 agents and then deploy this trained model into a scenario with 4 agents, it might actually perform just as well as if it was trained with 4 agents at the start. So in our use case, we're seeing 2 tables here. The rows of the tables represent the number of agents during training, and the columns of the table represent the number of agents during deployment and during testing in our case. So as you can see, our models perform adequately well when they're applied to a higher number of agents than they were trained with. So the 2 agent model, as you can see here on the first row and first column, it performs well on the, of course, it performs well on the 2 agent scenario, but it also performs quite well collecting like 96% of the time it collects all sensors and on the 4 agent scenario. But our models, they perform horribly when we try to apply them with less agents than they were trained with. And the reason for this is because like if you think about the inputs the agents are receiving, like the observations the agents are making during training, when an agent is being trained with, for example, 2 other agents, so 3 agents in total, it is accustomed to being able to observe 2 other agents at all times. If we deploy this model into like a 4 agent scenario where there is 3 other agents, each agent will independently still be observing 2 other agents. There will be an extra agent performing actions as well, but from the perspective of each specific agent, this third agent doesn't exist. So it's able to adequately perform in a way because it is being fed information that is similar to which it was fed during training. But if you reverse it and you apply, for example, a model that was trained in a 4 agent scenarios where it was accustomed to seeing 3 other agents. If you apply this model to a 2 agent scenario where only one other agent is present, like every single observation each of these agents will make is completely new to them because they were never exposed to a scenario where the number of agents was less than 3. So that's why the model performs quite bad when we try to apply them in a scenario with less agents. But overall, this is a promising strategy, especially if computational power for training is limited. So this is basically the end of the presentation. Uh, just summarizing a bit the contribution here. First, the adaptation of the multi-agent reinforcement learning algorithm for the data harvesting scenario, modeling the scenario as a continuous action and state space problem, and also implementing a decentralized solution for controlling the agents. The second contribution is the evaluation of the proposed strategy on the simulated scenario, and also the discussions about the scalability of the solution, the trade-offs between like quality and the computational resources used during training, and also the proposing some strategies to minimize the training resources. Thank you.